Hi everyone, welcome. In this video, we're going to talk about gravitational force. This is going to be very introductory kind of video in which we look at how gravitational force can affect the motion of the objects. So we will not go into the quantitative analysis of the gravitational force here. It's just to get the intuitive feel of gravitational force. So over here, we are considering two objects. Um, One is yellow color one and the other one is purple color one. Their masses can be reduced or increased, varied from 300 units to less than zero point 0.1 units, each one of them. So suppose I take each of them as equal, let's say 150 if I take, all right. Um, Both the masses are separated over here by a large distance. I'll show the measuring distance here. In the grid that we have here, one side length is 1 astronomical unit. 1 astronomical unit is equal to the average separation between Earth and the Sun. So this is right now you see the separation between these two objects is twice the astronomical unit. Such a large distance when you consider, right, you will not have nuclear forces. You don't have to worry about them. They'll be far negligible. And when you assume the objects to be neutral, then there would be no electric force and magnetic force. So the only force that is involved here is gravitational force of attraction between them, mutual attraction. And we are also assuming that these two particles or the two objects that we are dealing with are completely isolated from the surrounding. We are not considering any other forces acting on them. So the focus is only the mutual gravitational force of attraction. And you see the gravitational force of attraction can be shown in the form of a blue color arrow. I'll zoom it down a little. So you see the gravitation force is like that. So you see that both the bodies are experiencing same amount of gravitational force in magnitude, but they are in opposite direction. They form action-reaction Newton's third law pair, and they lie on a common line of action. So suppose I change the mass of one of the objects, let's say. Let's reduce the mass of the purple one. As the mass is reduced, you see that gravitation force on both of them is changing and both of them will experience the same magnitude of force. So gravitation force is equal on both of them in magnitude wise. Of course, direction is reverse. So it's not that heavier one experiences a larger force or the lighter one experiences a smaller force, but the gravitational force is actually directly proportional to the product of the both masses. So even if one mass is changed, overall gravitational force will change. And also you can change the separation between the objects. You can bring them away from each other and bring them closer to each other. So by changing the separation also, gravitational force can be changed. Closer they are, more is the gravitational force. Farther they are, lesser is the gravitational force. And you can also change the masses. By that process also you can change the gravitational force. Okay, so gravitational force is one parameter that we are looking at, which depends on both masses as well as the separation between them. Let's give some velocities to them. Let's say I'm giving some velocities like this. One is 2.34 kilometers per second and the other one is 23.45. In the ratio 1 is to 10, let's assume. And the velocities are also given opposite to each other. One is moved in y direction, the other is moved in negative y direction. Let's assume this particular one. And you also have a center of mass between them. Alright, center of mass would be lying on the line joining both the particles or both the objects. So first of all, let's remove the speeds and velocities just to focus on this center of mass. You see the center of mass would be in between. So suppose I make the masses to be equal. Let's say both of them are made 300 units. Now you see that the center of mass would be exactly in the middle. So when you have equal masses, center of mass will be in the middle. I'll remove the gravitational force also just to focus on the idea of center of mass. Now suppose let's say the mass of yellow object is reduced. As the mass of the yellow object is reduced, you see that the center of mass is going away from the yellow mass, the lighter mass. and it is going towards the heavier object. So as the mass decreases and decreases and decreases, when the mass becomes too small, yellow mass, then you see that the center of mass of the entire system is almost coinciding with the center of the purple object, which is the heavier one. When you have two objects, that's the case. All right. And in fact, the line joining these two objects is divided by the center of mass in the inverse ratio of their masses. Closer is the object, meaning heavier is the mass. So that's another idea of center of masses that we are looking at. So initially what we do is we'll take a very light yellow object and very heavy the purple object and let them run and see how they move. Let's see how they move. I'll remove the scale part of it over here. They are moving some complicated path. You see the purple one was going in a straight line path, but the yellow one went in a curvilinear path. Now if I see the same problems with respect to the center of mass, assuming a frame of reference, an observer is fixed to the center of mass and then you observe them, you see that center of mass will be stationary. Center of mass will be almost coinciding with the center of the purple object, which is the heavier one. And purple object is not moving, almost it is at rest. It's having a negligible velocity. And you see that the yellow one is moving approximately in a circular path. You can show velocity vectors also, all right, on the green arrow. It is always tangential to the path traced by the particle here. So you see that when the one object is heavy, you can assume it to be approximately stationary. Like for example, sun is so heavy. So mass of sun is so high as compared with the mass of the earth. So the motion of the sun can be neglected when you are studying the motion of the earth. That doesn't mean that the sun is not moving. It's actually moving, but the motion is negligible compared to the motion of the other particle, lighter object that we have here. As the masses are brought to be equal, let's say I'll bring the masses to be equal, then the motion would be very interesting, and of course center of mass would also be moving in this particular case. Let's observe the motion with respect to center of mass. So I think they went far away from each other. Maybe I'll review it again. Now let us observe this motion with respect to center of mass. See how they move. So now you see that both of them are going with equal speeds. Center of mass is in the middle. They seem to be going almost at a single path. The path is approximately circle now. At any moment, if you observe, are they having the same speeds? Yes, 12.9 and 12.9. At any other moment, 12.96 and 12.96. They see they'll have the equal velocities, magnitudes, but they'll be moving in opposite directions. So the total momentum is zero. They have equal masses and equal magnitude of momentum, but they are different directions, opposite directions here. So the net momentum is zero. And center of mass is stationary. Whenever center of mass is stationary and mass is constant, linear momentum of the system will remain zero. Okay, as they are running, okay, let's consider as they are running, let me change the masses. Let's say I move the masses and assume the center of mass to be fixed, and you see you will get very interesting paths. Of course, now it is not a circular path. They are having some complicated path. Let us see the entire path and observe it. Is it a circle? With respect to center of mass, will they go in circular path? It's not necessary that they should go in circular path. So if you observe them in a slow motion, all right, now you see when they are closest to the center of mass, this is where they are very close to the center of mass. I think almost that's the closest position. The yellow one has got a velocity 17.31 kilometers per second, and the purple one has got 8.6, where the heavier one will have a lesser radius of curvature. All right, at any moment. So that's what you have, 17.31 and 8.65, meaning approximately double, 1:2. Of course, you see the masses are also in the ratio 1:2. Fine. So when they go to some other location, at any other location, Let's observe them and see the speeds. Okay, let me stop over here and observe it. Now you see 15.33 and this is 7.67. So again you see it is almost like 1:2 ratio. Alright, so the speeds are in the ratio 1:2 and they are opposite each other because net momentum has to be 0, no? So m1 v1 bar plus m2 v2 bar together has to be 0. One is positive linear momentum if you take, the other one would be negative linear momentum. Alright, both of them are moving around center of mass. Center of mass is not necessarily at the center of the path here. So we can run it faster and observe it. So this is what I'm observing. Okay, at any other location, I'll change the masses slightly again. Let's look at it with respect to center of mass and see the path of them, how they move and all that. So how about changing the mass once again and see how they move? With respect to center of mass, I'm observing it. Okay. You see center of mass is taken to be frame of reference. With respect to center of mass, they are moving. How about now? You see center of mass also is allowed to move, then they go in a very nice spring like path. Alright, with respect to center of mass, when the center of mass is stationary, this is a path they are taking it now. And different masses you can take, you will have different paths. Can they cross each other? So if you look at the gravitational force, how it is acting, see, as they come closer and closer, the gravitational force increases. As they go farther away, the gravitation force decreases again. When they are farthest, you will see even the speeds are also least. As they come closer, they go more faster. So that's what when you consider the planetary motion, right? Earth would move fastest when it is closest to the sun. That is during the summer time. Earth would move slowest with respect to center of the sun when it is farthest, that is during the winter time. So this same understanding you can have it. So if you observe the binary stars, you might have studied about binary stars, where the binary stars move around the center of mass. Alright, with respect to center of mass, they move around it. And in fact they can actually converge. If the masses are sufficient, they can actually come closer to each other and merge into each other and then form a very spectacular visuals on the sky. All right, so that is something that we observe. So anyway, in this particular video I just wanted to show you how gravitational force qualitatively can be visualized and how the velocities would be affected because of the gravitational force. Alright, so with that I'll close here. I hope you understood the qualitative analysis of the gravitational force in this case. Thank you very much for watching and until next time, goodbye.